For example 1, we're looking at a system here which is going to end up being a first order system. It's basically a block of mass m which is able to slide on a horizontal surface. There's a harmonic force F of t which is being applied to the block, but between this horizontal surface and the block is a layer of viscous fluid, which we'll model as really a dashpot with a damping coefficient of c. And what we want to find is the steady state response for the velocity, and we want to make a plots of the amplitude and the phase. We'll talk more about what that means in just a bit. But let's start out with our usual procedure here of drawing an FBD. We have the applied force F. The damping here on the bottom, that's the sign convention for V is positive to the right. So the viscous force will oppose the motion to the right, so that's to the left, as that. So when we sum of forces acting on the block in X, I'll make this X and Y. We have minus the damping term plus the applied force, and that by Newton's second law is ma. Well, A in this case is just V dot. So what I will do then is I will put this equation in standard form by dividing through by the coefficient there in front of V, and then bring the V in the same side as the V dot. So this becomes a V dot m over c plus V is equal to the applied force F divided by c. And F was equal to F naught sine omega t, so that's an F naught over c sine omega t. Well, we have called this coefficient before the time constant of tau, so let's keep that same result. This here is what's called the gain there of k. So our normalized or our standard form of the equation of motion is tau v dot plus v is equal to k times our input, which I'll give that the name of u, k u of t. We are looking for steady state response. Steady state response comes only from the forced part. The forced part means that we can solve the problem with zero initial conditions and know that we haven't lost anything. So I take the Laplace transform of that, I get tau s plus 1 all times the Laplace transform speed there of v, and that's equal to k Laplace transform of our input. So our response transformed k over tau s plus 1. The Laplace transform of sine omega t is omega divided by s squared plus omega squared. So this, of course, is our transfer function g of s. That's going to play a very important role in our response. And this, of course, is the Laplace transform of our input there of u. Well, we know that a critical step in doing the inverse Laplace is that we first need to put it in its partial fraction expansion, which means we need to know the poles of our transformed response. So the poles in this case is we have one pole coming from G and two poles from U. From G, we'll call that P1 as minus 1 over tau. Again, this is coming from G of S. And then our input has two poles, P2 and P3. S squared plus omega squared equal to a 0 means that the two roots of that are plus or minus J omega. So again, these are the two poles that are coming from U of S. So the process that we have learned to like so well here is that we write V of S in terms of its partial fraction expansions, A1 divided by S minus P1. A2 divided by S minus P2 plus A3 divided by S minus P3. And again, we have complex poles coming from U, the complex conjugate pairs. That's always going to be the case for harmonic excitation, whether it be a cosine or a sine. And what we have seen many times before is that this is the same thing as complex conjugate of A2 divided by S minus the complex conjugate of pole P2. So what we have therefore is A1 divided by S minus P1 twice the real part of A2 divided by S minus P2. Very a standard thing by this point when we know that we have complex conjugate poles. So therefore, our process is to take the inverse Laplace of that. So we get the A1 EP1t. Then we get twice the real part of A2 EP2t. This is a transient term. Why is that? Well, have an exponential with a real exponent. Important thing is that the real exponent is a negative, so that dies away. So what's left here is going to be our steady state. So I'll call that VSS T. How this is different from the transient part is that P2 and P3 have a zero real part. So that's not going to die away. There's no decaying exponential term. So our procedure then is to evaluate a residue there of A2. A2, we know what we do is take S minus P2, multiply it by the transformed response V of S, and evaluate that at S equal to P2, which in this case is J omega. Okay. S minus P2. And if I go back up to V of S, we had V of S was equal to the transfer function G, and U of S was equal to omega. And if we factor out that form, S minus P2, S minus P3. And again, we evaluate that at S equal to J omega. That's simply because that's what P2 is. So that cancels with this. We get G evaluated at J omega. We have an omega divided by S, which is J omega, minus a minus J omega, because that's P3. So that ends up being G of J omega. And the omegas will cancel out here, so we get 1 over 2J. And if I convert that to its real and imaginary parts, I get minus J over 2 GJ omega. Now hopefully this process is familiar and there's no surprises here. But what I want to point out here is that this is likely the single most important step that we're going to use for the next 3 days of class. We evaluate the transfer function at J omega. Why is that? Well, that's just what the rules say. When we evaluate a residue here, we set S equal to that pole, and that pole was j omega. That's always going to be the case when we have sinusoidal excitation. So our process has been then that we take our complex residue there of A2, we multiply that complex exponential, we multiply through, we sort out real and imaginary parts and drop the imaginary part. What I want to propose here is something a little bit different. And a little bit different in that it's going to make our life a lot simpler. And the more important thing is that it gives us some physically understandable terms. So here is the change. What I'm going to do is recognize here that our transfer function gj omega, if we would plot that out in the complex plane, we plot the real part, which I'll just call gr, and the imaginary part gi. We'll come back in a bit and see what those actually are. But in the complex plane, we could write this as a vector, if you will. G, which is made up of real and imaginary parts. So G, j omega, just the real part, whatever that works out to be, plus j times the imaginary part. What we can do is instead of writing it in sort of a Cartesian form, real and imaginary parts, we could change this over. We could say, well, we're going to write this as the modulus, the length of this vector, that's this amount here, times cosine of this angle. Right now I'm going to call it phi. And then there's j times g omega t, or g j omega. That's the imaginary part when we multiply that by sine of phi. So this is sort of a polar description of gr. This is a polar description of gi. If we factor out the gj omega, we have a cosine phi plus j sine phi. Euler's identity tells us that this is e j phi. So this is the long way of basically saying, instead of writing it in a Cartesian real and imaginary parts, I'm going to write it in a polar description of a magnitude, a radius, if you will, the magnitude times the complex exponential. So this is a result that we can just sort of see from the picture. It's one that's used quite a bit to convert from one form to the other. And I'll finish this out by saying, if you look at the picture, the magnitude of that vector, complex vector, is the square root of the real part squared plus the imaginary part squared, added together with the square root. And phi here is the inverse tan of the imaginary part divided by the real part. That you can see from that right triangle there. And this is something we're going to use a lot, regardless of whether it's a first order system, a second, or whatever. And you might recall that when you use the inverse tan, you have to be very careful to get the right quadrant of the angle. If you just divide the two numbers and hit a tan on your calculator, you're only going to get an angle between minus pi over 2 and plus pi over 2. Maybe the phase angle is going to be someplace else. The way to ensure this is either draw a picture, make sure you got the right quadrant, or you use that MATLAB function a tan 2, where you give it the imaginary part and the real part is two arguments, and that will give you a four-quadrant representation of that phase angle. Anyway, where are we going? Recall that what we want to find is the steady state response there, V. We got rid of our transient term. That was 2 times the real part of A2 EP2T. That hasn't changed. That's still as it was before. But here is where we'll take advantage of our polar form. We got 2 times the real part of A2. A2 was, what, minus J over 2 G J omega E P2 T. Okay, so now this is where we take advantage of this. This becomes magnitude modulus of G times E J phi. Okay, I can also convert this term here to a polar form. That one ends up being E, in fact, if I put the minus sign in there, it's E minus J pi over 2. Basically doing the same thing that this number here, minus J, that's going to be an angle of minus pi over 2. And J has a modulus of 1, so there's a 1 that goes out in the front. The 2, I shouldn't have included the 2 in there. That 2 cancels out there. So the point being is we got real part still of an exponential, and an exponential. All times are modulus there for G. So we know the product of these 3 exponentials is going to be the exponential of the sum. Keep in mind here that P2 was J omega. So this is E to the J omega T plus phi minus pi over 2. Like that. And again, this is, once you have it in the polar form, this is a much easier process than what we did before of multiplying complex residue times a complex exponential. We can bring this out on the outside because the modulus is always real. So this is E, J, omega T modulus. The real part of this, well, the real part of that's just cosine. Cosine omega T plus phi minus pi over 2. And we know that if we phase shift a cosine by minus pi over 2, it's the sine omega T plus phi. So this is a very important result, not only for this example, but for all the other problems we're going to look at in this chapter. And it tells us a lot. It says that we don't have to go through the partial fraction expansion. We don't need to do an evaluation of residue. All we need is to know the transfer function G, set S equal to J omega, take the magnitude of that. I think that gives us the magnitude of the response. Phi here, that's the phase angle that goes with J omega, E J omega. So again, both of these come from the same thing. If you know the transfer function, just set S equal to J omega, get the magnitude of that gives you the magnitude of the response. Find the phase angle, that's the phase angle of the response. So the process is less involved, it's more physically insightful in the end. For our particular problem, though, if I write out this, I take the real part of G. If I look back up in my notes, the real part of G. Well, maybe I haven't even written this out yet, have I? So let me do that. E G J omega, that's K omega n squared, divided by, looks like I don't have this here in my notes, so let me try this one more time. This is actually K on top. I have tau times J omega plus 1. So that's K 1 plus J tau omega. In order to get this in real and imaginary parts, I multiply top and bottom by 1 minus J tau omega. So what I get on the bottom is a 1 plus tau omega squared. I can get K times 1 minus J tau omega, like that. So from this I can see that the modulus, the sum of the squares of the real and imaginary parts with the square root, that's going to be a 1 plus a tau omega squared, like this, divided by 1 plus tau omega squared times K, and that ends up therefore as being K divided by the square root of 1 plus tau omega squared. The phase angle, phi, is the inverse tan of the imaginary part. The imaginary part we see was a minus K tau omega. The real part was a K, so that's the inverse tan of minus tau omega, and I'm going to keep the 1 in there just to emphasize that if you did use the a tan 2 function, you would have minus tau omega followed by a 1. So our last step here is to plot the magnitude and the phase as a function of omega. So if we go back to our plots, you will find that the amplitude starts out at a K. It drops off like this. Whenever you draw it, be sure that you draw a zero slope here at the top. And the phase angle starts out at a 0. It goes down to a minus pi over 2, like this. So the phase angle is always a negative here. It starts out at a 0. The phase increases up to minus 90 degrees as you increase the frequency. The interpretation, well, if you think about this, if you apply a force to a block like this, for low frequency, basically the block's going to be going back and forth with some finite amplitude. But as you increase the frequency, the mass is such that it doesn't have time to respond if you apply that force too fast. So as you make the frequency large, you're not really giving the mass enough time to respond. So it basically looks like it's a stationary. It's a very small amplitude of response. Anyway, this example, very long for a very short example, but it serves as a motivation for the rest of the examples we're going to do. It serves as a motivation actually for the theory that we'll talk about in a lecture for both first order and second order systems.